So I'm Jeremy Mao. I'm here with Team 2, and our presentation is on lightmatter, the company, and photonic computing. So as engineers, we feel that it's a good idea to first find the problem that we're actually trying to solve before going to the solution. So before we even start talking about lightmatter or photonic computing, we first want to discover what problem are we facing with the solution. So right now, we're currently in the age of artificial intelligence. And these large language models require billions of parameters, and as a result, require a huge amount of energy and computational power. And there's no magical way to just scale computing power into existence, at least not anymore. Before, the traditional way to increase or scale computational power was by shrinking down transistors to be as small as they can. But Moore's law is ending, and so is Dennard's scaling law, and so that is no longer the name of the game. It's no longer just scale down transistors. So the solution to this is innovation and new products. So what is one of these set of solutions? Photonic computing has been around for 60 years in the making, and the basic idea is that instead of electronic data management, you use light, you use photons. So in theory, each operation happens at the speed of light, and that greatly reduces the buildup and slowdown in the interconnects, or the physical or logical pathways that share data. So what lightmatter startup is doing is that they're designing chips for data centers and other applications that integrate this photonic computing technology, or co-packaged optics, into XPUs like CPUs and GPUs and switches.
So this is Envise, which is lightmatter's photonic computing chip. And unlike traditional processors, Envise doesn't rely purely on electrical signals. It combines both optical and electronic circuits on the same chip to boost speed and efficiency. And so the idea is to delegate tasks based on what each component does best. So transistors, they handle memory, storage, and logic control. And the photonic elements like the lasers and the modulators, they do the hard part that includes all the math that goes into the matrix multiplications. And so Envise is a full system-on-chip application. It's a hybrid that can run AI workloads with incredible efficiency and scale. And so, next slide. In terms of how it works, it's built with silicon photonics, meaning that it uses optical circuits made on silicon wafers using the traditional chip making tools. And so the benefit of that is it's scalable and manufacturable at an industry scale. And what sets this chip apart is how it performs operations. It leverages interferometers and wavelength division multiplexing, also known as WDM. And so what it basically does, as you can see here, it allows it to send multiple streams of information at the same time, each one traveling on a different wavelength of light. And so it's like a highway where there's each lane is a different wavelength, and instead of just running one operation at a time, it can run many in parallel on the same hardware. Next slide. And so inside the chip, you have 256 RISC CPU cores and a photonic matrix accelerator. You also get 500 megabytes of SRAM on chip, and this minimizes the bottlenecks that come with traditional chips in terms of memory. And the photonic side acts as a matrix math accelerator, and it's optimized for AI types like int8, int16, and vfloat. And these are all common in neural networks. And what's especially unique is the way Envise chips scale together. Each one has a 400 gigabit per second interconnect, which lets you connect these different chips together, and it runs as if it were one giant processor. Next slide. And then the best thing about it is the ease of use. It's manufactured using standard CMOS fabs, the same things that make GPUs and CPUs. And on the software side, Envise comes with the Idiom software stack, which includes debugging tools to translate AI models, and it also integrates TensorFlow and PyTorch directly within the model itself, so you don't have to learn anything new.
So today I want to talk about lightmatter chips specifically for AI applications. So lightmatter's photonic chips are purposely built to support these artificial intelligence workloads, and especially in the deep learning realm. So Envise is actually described as the world's first general-purpose photonic AI accelerator, and is capable of running cutting-edge neural networks such as LLMs, transformers, recommendation models, and computer vision networks with very high throughput. And these tasks range from image recognition to natural language processing, and Vyse is able to do these processes much faster due to the photonic hardware in comparison to electronic processors. So just some use cases for photonic chips. So lightmatter's photonic chip technology allows a lot more use cases to be more efficient, ranging from the automotive industry to the healthcare field. So one example is in autonomous driving. So photonic chips can power the real-time vision and sensor technology within cars and data centers. In robotics, same technology can be used to accelerate vision and control algorithms. And in the healthcare industry, these AI models can benefit fields of drug discovery and image analysis. And in finance, these recommendation models can bolster risk analysis models too. Essentially, just in any AI use case that's constrained by any sort of hardware or compute speed or power consumption can be benefited with lightmatter's photonic chips. So how does Vyse stack up against other sort of CPUs and memory? So lightmatter's Vyse 4U photonic server blade contains 16 Vyse photonic chips, plus these conventional host CPUs and memory. And the blade basically achieves up to 3 times higher inference throughput than NVIDIA's servers, which uses 8 A100 GPUs and only uses about half the power, so it's much more efficient. So in a benchmark test that's conducted with a BERT language model, which is a model that allows computers to recognize natural language, and the Stanford question answering data set, which is a data set that's meant for computers to learn how to read. Lightmatter's 16-chip photonic blade reaches 3 times the queries per second of an 8 GPU system, so it's much more energy efficient. Finally, so deployment and adoption in the field. So a lot of customers are sampling on Vyse blades to evaluate performance, especially on large language models. And these blades are envisioned as the next AI supercomputers. So lightmatter's photonic chips are basically just finding use cases wherever AI workloads are pushing limits of conventional hardware.
All right, as we sort of enter this new age of AI infrastructure, there's an increasing demand for GPU clusters. As you can see, all the companies like Microsoft, Amazon are building these big data centers, and they're filled with hundreds and thousands of GPUs, and they sort of need a better way to communicate with each other. And this is sort of what lightmatter solves in terms of latency, because light or photonic communication is a lot quicker than electronic communication, because electronics, they have certain walls and constrictions that come with the copper interconnects. And so photonic communications, they can achieve bandwidths on the tens or even hundreds of thousands of terabits per second. In comparison with NVIDIA's current NVLink, which is state of the art, they can only do about 0.9 terabytes per second per link. So it's a lot quicker, and a lot of these companies are trying to find an alternative way to sort of solve this slowing of the scaling law when it comes to electronic interconnects, and photonics is a possible solution. So what does photonics sort of do with, how does it scale with AI models? So lightmatter architecture can scale linearly, which basically means that you can add more photonics chips while maintaining performance without greatly increasing energy usage or cost. Energy usage is a big problem when it comes to these data centers. They take up a lot of energy, and as many of you know, that some of these companies are looking into nuclear energy to solve these energy usages, but nuclear is a very controversial sort of energy method. So lightmatter, once again, is another solution of addressing this energy problem. And so optical matrix multiplications, which are a fundamental operation for all these AI models, is naturally scalable, or is naturally parallelizable in photonic hardware. And these what makes these optical internets so good is that they're able to do all these operations simultaneously, so there's no latency. And each photonic core can handle a portion of the computation independently, so you can scale the architecture simply by adding more cores. So it means it's modular and has linear performance expansion.
So looking into the comparisons and future implications for computing of Lightmatter's photonics chips, the first thing that we found out is that they deliver significantly higher speed and efficiency for AI inference and AI training tasks compared to traditional methods using traditional CPUs and GPUs. So that means that with Lightmatter's implemented photonics chips, they could have a major reduction in AI model training times. Another major benefit of photonics chips is that they remove barriers for data exchange bandwidths, so that leads to lower latency throughout the system and reduce bottlenecks, which means that you can scale your data centers even larger. And looking further into the future outlook, for short-term future outlook, one of the things we found out is that photonics, we believe in the future that photonics will complement CPUs and GPUs by acting as the connector between different GPUs and CPUs, which, like I mentioned earlier, allows for lower latency and can lead to further scalability of data centers. Looking into the long-term goals, however, photonics technology could redefine computer architecture, and many components will start using optical technology like Lightmatter's chips. And there's also a major positive environmental impact for photonics chips as they lead to reduced heat and energy usage while delivering the same results. And looking finally into some challenges that photonics chips face, the first is going to be manufacturing consistency and scalability, as this is relatively new technology and lots of manufacturing tools and techniques have not been discovered yet. Furthermore, the creation of standards in photonics is also necessary, as they'll allow lots of new companies to build up even better photonics chips in the future. And lastly, another challenge would be integration of photonics and traditional electronic elements, which is what we mentioned in our short-term goals. That needs a lot more work in order to ensure the maximum efficiency between photonics and traditional electronic components.